Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, which was published in 2024. More specifically, we are looking at chapter 7, which is about the fate of heat in lakes and rivers. And today we'll be looking at oligomixes, and we'll probably be ending the chapter today. Oligomixes occurs among lakes of small surface area and moderate depth that are sheltered, especially in continental regions that experience long winters. In such location, a dynamic lake may skip a circulation period, usually in spring, and increase solutes from decomposition in the lower strata of the lake can persist under unusual weather conditions. For example, in lakes in which solutes accumulate near the bottom during winter and near bottom temperatures are slightly above or below 4 degrees centigrade, mixing in spring may be incomplete, and stratification can persist for much of the summer. Persistent stratification at ice-off in the week following is illustrated for 3 Arctic lakes in figure 7-31. The rapid downward mixing of heat at ice-off that precluded full mixing in the smaller of this lake is described in Cortez and McIntyre. Near bottom chemical stratification persists in the smaller lakes for much of the summer, whereas when the fetch is longer, as in Toolik Lake, near bottom pycnoclines can be eroded more rapidly. So they're saying that persistent stratification at ice-off and in the week following is illustrated for 3 Arctic lakes, 731. So let's look at that here. It kind of goes back a ways, but we can look at it. Let's see. So this is figure 733, 731. Here we go. So they are saying that stratification is maintained for those 3 Arctic lakes, especially, I believe, for N2 and E1 after ice-off. So ice-off occurs, let's see, so this is in temperature. We have the temperature here. We have day of the year from 2010, and we have 3 graphs. And these 3 graphs, I believe, let's see, thermostructures and time series changes during winter, leftmost panels, fall, middle, and shortly after ice-off, right panel. Okay. So shortly after ice-off for N2 and E1, we have like currently like the ice-off period where we don't have much stratification occurring, and then we have persistent stratification right here that occurs before the heating events. This is what they're talking about, which is due to some degree to chemical-based stratification. So which probably is ice-off can be identified in spring as the time when temperature rapidly increased in the upper water column because of the increased density from increased solutes in the lower water column. All these 3 lakes and additional density gradients as snow melts freshen near surface water, mixing from penetrative convective prior to and at ice-off either did not occur or did not penetrate through the full water column. So so they are saying that, like, so this is, like there's the layer of ice, the ice melts, and we have some freshwater inputs, but we have denser water, high density water here due to input from probably geothermal or other drivers that are preventing stratification mixing to occur. Okay. All right. Let's go back where we are. Human and natural causes led to oligomixes in endorheic monolake. Meromixes results from increased inputs of freshwater in years with large snowpack in the adjacent Sierra Nevada and from reduced diversions of incoming stream water. The freshening of the upper water column creates chemical stratification Precipitation patterns in California vary over the years, sometimes with a snowpack up to 300% of average, followed by several years with below average precipitation. Evaporation during the summer is high. The resulting increases in solutes, the resulting increases in solute in the mixolimnion during drought years reduce the density gradient between the mixolimnion and monomolimnion, such that monomixis is again established. Stratification in Mono Lake has features in common with Lake Kivu in that there is an upper oxygenated layer with chemoclines below. These gradients and accompanying variations in solute create habitats favorable for a wide range of microbes that occupy discrete layers according to redox condition and either oxidize or reduce the substrates. So let's look at that figure here. Figure 7-43. Density differences between 2 and 28 meters depth in Mono Lake due to thermal stratification from seasonal variation in temperature, chemical stratification due to the freshening of the upper water column, and total stratification, that is the sum of the two contributions between year variation in thermal stratification and minor. Persistent stratification, so they're telling us that that thermal stratification is not as much of a driver than chemical stratification. Persistent stratification was induced in 1983 due to the increased chemical stratification due to runoff from a snowpack. So it's kind of a little counterintuitive in the sense that with increased snowpack, we have like an increase in freshwater inputs to the lake. However, that less dense water is above the denser water that is that has a higher concentration in solute, and that is decreasing the stratification during that time due to increased due to runoff. Seasonal mixing was restored in 1988 as increased solute from evaporation during summer reduced the chemical stratification during years with below average snowpack. Persistent stratification was induced again in 1995 with reduction in water diversion to the city of Los Angeles. So this is the anthropogenic input, with chemical stratification further accentuated with increased runoff from elevated snowpack in 1997, which persisted until 2004. So here we have the x-axis, we have the years, so between 1980 and 2010, so that spans about 30 years, so actually this is 11 and maybe 12, so maybe 32 years. And then we have density difference between 2 meters and deep water in kilograms per meter cube. The total stratification is in black. The thermal stratification is the small little lines here that are like seasonal based stratification. And then we have the chemical stratification in the dashed lines. So what we're saying is that during El Nino years, for example in 1983, we have a chemical stratification that persists, as well as in the late 1990s and up to 2004, we have chemical stratification, which drives the total stratification. So when we have chemical stratification in Mono Lake, we also have total stratification of the lake as well. And so therefore, as we were saying, the thermal stratification is a low driver compared, or has lower priority in terms of stratifying the waters than the chemical stratification component. And counterintuitively, when we have like an El Nino year, when we have inputs of fresh water, that actually drives the stratification and maintains the stratification because we have fresh water over salt water, and it's preventing the mixing of those two layers. All right. Changes in seasonal and annual stratification with climate change. Shifts in stratification regimes have been observed over long periods. However, the current concerns are changes in temperature and mixing regimes, and modification of the thermal habitat of organisms in lakes as air temperatures warm with recent climate change. Changes within lakes may also vary over time, from cyclic changes in meteorological forcing due to atmospheric cycles, such as the El Nino Southern Oscillation, North Atlantic Oscillation, Pacific Decadal Oscillation, and the Arctic Oscillation. Thus, assessing change due to climate warming requires data collected over time periods that exceed the higher frequency changes from these cycles. Changes in heat content may be independent of changes in lake surface water temperatures, indicating that changes in lake surface water temperatures may not always be the correct metric to assess responses to climate change. In addition to increasing temperature, some regions are experiencing increased precipitation, others less. The timing of precipitation is also changing, with some cases less as snow and more as rain. Changes in precipitation and changes in land use can together modify the loading of solutes and particulates, which influence the optical properties of water. Increasing in attenuation coefficients lead to more heat being absorbed in the upper water column and an intensification of stratification, whereas decreases lead to deeper mixed layers. In other cases, decreases in water level combined with slight increases in air temperature in some seasons lead to near surface warming. The integrated effects of these and other changing variables on the future states of lakes can be predicted using hydrodynamic models, a topic discussed in Chapter 8. The following is a brief summary of changes or expected changes in mixing dynamics on a regional basis for a comprehensive assessment of climate change effects on diverse lakes and rivers. See Goldman. In the high Arctic, partial loss of ice cover in previously amictic lakes, so lakes that don't mix, has led to cold monomixes in some years, so lakes that just mix once, with consequences for the stability of near-bottom sediment with their extensive cyanobacterial mats. In high Arctic, Lake Hazen on Ellesmere Island, Nunavut in Canada, the mean daily ice-free area from early May to early September ranged from 45 to 65% from 2000 to 2012, with an overall increase in open water, which led to concomitant increases in pelagic diatoms. For smaller Arctic water bodies, the increased temperature led to increased evaporation and the loss of ponds. Many small lakes in the subarctic are currently dimectic and based on their lake numbers and are in regime in which wind-driven mixing will persist. However, in years in which synoptic activity is reduced, the enhanced winds associated with frontal system do not occur. Hence, lake numbers remain above 10 for much of the ice-free periods, such that heat is retained in the upper mixed layer and the meta-limnion thickens. Thus, shifts in meteorological patterns can induce shifts in mixing dynamics in subarctic lakes, such that they are more like those in similarly sized temperate lakes. Water temperatures under the ice depend on summer air temperatures and heat losses in fall, as they modify the heating of the sediments as well as direct solar heating. With increased heat in sediments, near bottom stratification with anoxia may occur over larger volume, with concomitant effects on concentrations of climate-forcing trace gases and loss of habitat for fish. These changes can occur in dimectic lakes. In many monomictic and deep lakes, temperatures have warmed over time and the period of stratification has lengthened. In some cases, the changes may be due to anthropomorphic influences rather than from changing air temperatures. The combination of stronger and more persistent stratification in temperate lakes has led to greater oxygen drawdown in the lower water column with diverse ecosystem implications. In northern lakes with increased heat content in summer, a longer period is required in autumn to cool lakes. Such delays combined with warmer autumn and winter air temperatures could then lead to warmer minimum lake temperatures and delay in the onset of inverse temperature stratification and ice-on. Combined with overall warming such that ice-off is earlier, the duration of ice cover has decreased and will decrease with projected climate warming. In many lakes, ice may no longer form and dimectic lakes will become monomictic. For deeper lakes in which ice does not form, for example, Lake Tahoe, Lake Taupo, and Lake Biwa, the concern is that they will not fully mix with an accompanying loss of oxygen in the lower water column. A number of deep lakes in Central Europe and Japan either are shifting or have shifted from holomictic to oligomictic. For example, complete mixing in Lake Geneva is expected to shift from once every 4.5 years to once every 8 years. Anoxia is building up in the lower water column in winter, and with previous attempts to reduce eutrophication in these lakes, shifts in nutrient stoichiometry have occurred with the combined effect of a loss of centric diatoms in the spring blooms, and increase in concentration of cyanobacteria, particularly in autumn, with consequences for higher trophic levels. In high altitude tropical lakes, deeper than 17 meters, stratification has shifted from polymictic to stratified for periods of several months over the last few decades. Results from deep lakes illustrate the importance of evaluating heat content to identify change and the variability associated with ensocycles. The changing meteorological conditions over Lake Michigan over the past 75 years have led to increased heat being mixed downward, a shortened period of overturning, warmer temperatures at the onset of stratification in spring, and a longer period of stratification with warmer temperatures. In a global study with 26 lakes of differing sizes, increases in heat content and Schmidt stability were larger in deeper lakes such as the East African Great Lakes, even though changes in surface temperature of such lakes were more muted. Metrics such as the Vedder burn and lake numbers may contribute toward determining if the ecological functioning of such lakes has changed. For Lake Tanganyika, calculated values of W during the southeast monsoon are less than 1. The result is obtained for calculating density using temperatures near the surface and at 150 meters and an upper mixed layer depth of 50 meters just before the monsoon, and mean wind speed of 5 meters per second at the start of and during the monsoon. The result implies that considerable tilting of the thermoclines can occur. Heat can be mixed downward, and recycled nutrients can be mixed upward to support productivity. Of additional importance for assessing change, the depth and or duration of mixing in tropical East African lakes depend on the duration of winds in the southeast monsoon, which varies with ensocycles. For example, the depth of mixing during the southeast monsoon in Lake Tanganyika was 200 meters in some years and 100 meters in others. Such variability adds further challenges to quantifying long-term changes to mixing dynamics. Continued efforts are required to evaluate changes in the mixing dynamics of these large, deep lakes, as well as lakes of other sizes, in order to evaluate the influence of climate on their ecological functioning. The efforts in the studies referenced above point to the value of and need for long-term monitoring data to assess the effect of climate and land use change on the mixing dynamics of lakes and resulting ecosystem changes. Summary. So let's go over that pretty quickly. I'll let you, read on further, but I'm just going to read the first few sentences of what jumps at me here, because we already reviewed that content anyway. The absorption of incoming solar radiation leads to the heating of inland waters, and in lakes, heat is distributed and altered by a number of coupled physical processes. Temperature depends on heat stored in a volume of water. Heat is measured in joules and is the product of the mass of the substance in kilogram, temperature, and the specific heat. Temperatures of streams, rivers, and lakes change over diel, seasonal, and annual cycles. So diel, once again, is day-based. Annual variability in surface and mean temperature tends to increase with greater latitude and altitude. Heat inputs results from several processes: direct absorption, incoming long-wave radiation, transfer of heat, condensation, transfer of heat from sediments, heat transfer from terrestrial sources. Heat losses occur by conduction, evaporation, outgoing long-wave radiation, outflows. Surface energy budget and heat budgets are computed to determine the contribution of ambient meteorology and advective flows to the heating and cooling of lakes and other water bodies. Heat budgets within water bodies are computed from temperature profiles or time series temperature data with sensors at multiple depths. Mixing will distribute heat in a lake as surface waters cool, causing convection, and as wind induces currents and shear. Seasonal thermal stratification occurs in most lakes of moderate depth. During warmer periods of the year, the surface waters are heated, largely by solar radiation, more rapidly than the heat is distributed by mixing. Lakes become stratified into multiple zones: the epilimnion, the hypolimnion, and the metalimnion. The seasonal thermocline can be defined as the plane or surface of the maximum rate of decrease or of temperature in the metalimnion, and can be identified as the depth where the buoyancy frequency is highest within the metalimnion, which is the N number. The resistance of a lake density stratification to mixing depends on stability, which varies with the distribution of heat and solids in a lake. Heat budgets enable stability, the likelihood of mixing. A number of metrics are used. For a lake as a whole, Schmidt stability, ST, is the quantity of work or mechanical energy per unit area required to mix the entire volume of water to a uniform temperature. The buoyancy frequency, N, and radians per second or cycles per hour quantify the depth, the extent of stratification as a function of depth. Typically, it would be least in the upper mixed layer with values close to 0 at night, and also low in the bottom boundary layers. However, over a diel cycle of stratification, a mixing value of values of N are highly variables in the upper mixed layer and in diurnal thermocline, often exceeding 20 cph or cycle per hour. So we'll let you read on to that N value here. And Vandenberg and lake numbers provide a dynamic assessment of the stability of a lake. These numbers take into account the stratification across the thermocline, the depth of the center of gravity relative to the surface or depth of the lake, wind shear. Vandenberg numbers can also be computed for diurnal thermocline. High values, that is greater than 10, indicate strong resistance to wind mixing and a stable system. So high value means stable system, and for both the Vandenberg and lake numbers. The coefficient of AD diffusivity is an indicator of the efficacy of mixing and is used to compute fluxes of heat and of scalars used such as nutrients and dissolved gases. Hence, estimates of Kz are valuable in biogeochemical studies, and when computing lake metabolism using the heat budget method, Kz can be computed for depth below the upper mixed layer. So other approaches are used for the upper mixed layer. Highest value of Kz are typically found in the upper mixed layer, and lowest values occurs in the thermocline. Variability occurs in response. Values of Kz in the stratified region can be predicted from lake and Vandenberg numbers. Loss of stratification toward the end of the stratified periods occurs when heat losses consistently exceed heat inputs of a diel cycle. Surface waters of the epilimnion cool become denser, and when denser than the water below, mix with water below. Not the best sentence here. Ice cover can form on the surface under cold conditions in cold regions. Inverse temperature stratification results when temperature decreases below 4 degrees C, the temperature of maximum density. As solar radiation increases in the spring, mixing may occur under the ice or may be induced after ice-off as temperatures increase and cause instability, often leading to full or partial turnover of the water column. Lakes undergoing complete circulation twice in a 12-month period, separated by periods of thermal stratification, are classified as dimictic. The layers in meromictic lakes are called mixolimnion, which is the upper layer that stratifies and mixes over diel and seasonal cycles. Monimolimnion, the deeper stratum of water that is isolated, and the pycnocline, the density gradient between the mixolimnion and the monimolimnion. And let's see, maybe we jumped a little bit here, so we didn't go over many other types of density stratification patterns occur due to the interacting effect of climate. These include amictic lakes that are permanently ice covered. Then we have do not foresee circulating vertical each year, and lakes classified as holomictic, meaning that they fully circulate in the vertical at least once a year. Monomictic lakes have one period of circulation, and polymictic lakes mix multiple times a year. And so holomictic, they mean that they fully circulate in the vertical at least once a year. Yeah, I mean, these include amictic lakes do not mix at all, and holomictic actually in some cases like mix like every 3 to 4 years, and not necessarily every year. Climate change is having multiple direct and indirect effects on lakes associated with the warming of surface waters, later onset and earlier loss of seasonal ice cover, longer periods of stratification, and reduced mixing of surface with bottom waters. And I think that's going to be it for chapter 7. So thanks for sticking on with me. This was a pretty intense and complex and information-rich chapter. Hopefully you enjoyed it, and we'll see you soon for chapter 8. Take care. Thanks.